Thank you very much. Can you hear me well? All right, so thank you, first of all, to organizers for putting this summit together. This is really interesting, lots of great talks, a lot of interesting people. In our talk, we're going to share with you our experience and some of the tools that we built for monitoring Spark jobs and basically taking the Spark applications into production. So this is work presented by myself and Ed Barnes, but also Chris McCubbin, who is our Director of Analytics, is right here. He's, right, in case you have questions, he's the main driving force behind innovations happening in our company. Ed is performance architect, so he's going to talk about more specific tools that we built. And I'm a senior data scientist. I'm building machine learning applications. So first of all, let me give you a little bit, 2-minute overview of what Squirrel is. Squirrel Data is a startup here in Cambridge. We're building a cybersecurity hunting platform. The idea behind the platform is to allow cybersecurity analysts to find the advanced persistent threats in the environment and target them and basically eliminate them in a prompt manner. So the main platform consists of distributed database, which is a cumular and supplemented with the various convenience APIs, query languages, etc. So the platform allows cybersecurity analysts to ingest various sets of data, logs, net flow, proxy, anything you can think about, the endpoint logs that can tell you about which processes are running on which computers, etc. All of this data is being ingested, and also, what we add on it, in addition to just ingesting the data, is ability for analysts to view the data in a more cybersecurity-centric way. We take the data and build a graph by connecting the data points that are often lives in separate logs, which allows users to look and explore data in a much more convenient way, allows them to see immediate connections between very different data samples. We also build composite entities, for example, time series, etc., by aggregating various logs that otherwise consist of many thousands of or even millions of records. So all of this is driven with the idea of allowing analysts to immediately get to the important data in the network that allows them to actually find the malicious behaviors. In addition to all of these, we're building a set of the machine learning algorithms that are designed to analyze the incoming data and find the malicious behaviors in this data. So combined with the ability to view the data in a convenient way and machine learning algorithms that tell analysts this is something which looks like possibly malicious behavior with the high statistical significance, look there, and then analysts can focus the attention to very small subsets of the data, do the exploration, find the actual attacks, and then ultimately do the response. So that's in a nutshell what the platform is. You can give a whole different talk about how we actually use the algorithms, what we build, etc. But this is not the topic of today. Not sure if I'm doing that or not. All right, now concentrating on just the machine learning part, this is where we use Spark. Our typical machine learning application it's run on a Yarn cluster, and it consists of roughly the following basic workflow. So we get the data from the distributed database. We ingest it, transform, load. Then we typically perform prediction by taking the pre-trained models. And then we record various statistics and ultimately write back our conclusions, the analyzed data derived from what we analyze the actual results back to the database and make it so that it would be available for analysts to look at. In parallel, you have several steps that actually do the machine learning training. This is done in we split up these two tracks so that to increase robustness and performance of the algorithms. Now, when we implement this in production, we ended up mixing Python and Scala code, depending on which one works best for the particular application. So overall, this is just to give you an idea that the typical Spark application consists of multiple stages, multiple jobs, and it's a mix of Scala and Python code. All right, then when you're ready, you wrote your Spark code, then now you're thinking, okay, I'm ready to take it into production. What are the things that you really have to think about? The first thing is the execution framework. Something has to launch this job. This job has to be monitored, run, and then ultimately completed, etc. So we built our own framework for that, and it works well, at least for our purposes. Next thing is you have to really verify that your application is scalable, robust, and very well tested. So many things can be done with the unit tests, but ultimately, it's extremely important to test at scale because many of the issues showing up only at that level. Only when you switch from gigabytes to 100 gigabytes to terabytes of data, this is when the whole new set of problems might be showing up that you have not observed before. And thus, we pay a lot of attention to testing at scale. What we're looking when we do that, performance, first of all. The scaling has to be predictable. We should make sure that as we ingesting more data, that our algorithm is able to process them, and also that it's not running out of memory and it's not taking increasingly longer time to do that, provided the matching resources. So memory requirements is extremely important. Failures, some of the failures only show up at the large data volumes. And ultimately, what you want to get at the end is the predictable scaling behavior. So these are the things that we typically look for in our scaling tests. Now, there's the final remark here is that most of you who have been dealing with the distributed application already know that debugging applications is really hard. So I'm going to give you a couple of examples of the issues that we had to deal with, and then show you how we use the current Spark UI and also additional tools that we built in order to understand these issues and deal with them. So first of all, typical failure mode is your job failed in Yarn, and you're trying to understand, okay, what happened? So the starting point typically is the Spark UI, which is a very convenient way to look at your Spark application. The first view is at the job level. So you have multiple jobs that has been already run, and ultimately, this is the job that failed. So first of all, it tells you already roughly the place in your code where a problem occurred, so that helps you. Then you can dive deeper at the task level. At the task level, Spark UI actually shows you the DAG that it has been running as a part of this job, and also individual tasks. And among, I'm not showing you the whole table, it's pretty big, but among various tasks that it ran, there is one that tells us that it's run out of memory. So in this particular case, the issue was related to a very large partition, initially very large partition of RDD in which we loaded our data, resulted into failure when we were performing a reduce by key operation. So these type of errors happening all the time, and Spark UI helps you to track them down and sort of pinpoint to the place in the code. What it doesn't help you is to verify that after you fixed it. In this particular case, the fix was to repartition and make sure that all partitions are small enough and evenly distributed. And when you start testing your solution, what you want to verify is that this solution actually gives you that scaling behavior that you're looking for. So if bad things are not happening, what is my memory usage, right, for each task. So what we want to see is that after we fix the issue, that it actually behaves as it should. So this is something that is not easily available for the Spark UI, and this is one of the reasons that we had to build additional tools for monitoring the Spark jobs. Another case, which was much more complicated, was I dubbed it as spitefulJ issue. And this is how it happened. One morning I come and all of a sudden I get this Slack message from our testing engineer. He's saying, oh my God, the code is blowing up all of a sudden when I ingest X amount of data. It was working well, now it's not. So what happens? And Spark UI does not tell us much. Something happened in between the tasks somewhere and we're really at loss. So this is where we really realize that we need, the only thing that in logs that we see is that there is obscure message there is somewhere down the stack trace we see, oh, Java heap space memory out of error, probably something ran out of memory. Okay, that's the amount of information that we got at this point. So this is where I'm going to hand over to Ed, and he's going to tell you about the tools that we built that allows you to handle such complicated cases.
That's great. Thank you, Ruslan. Can everybody hear me? So as part of a tooling approach for this problem, we have this distributed system. It's running on an HDFS cluster. We've got our Squirrel servers that are running on all of these nodes as well. And we're running Spark under Yarn. So we needed to come up with a solution to give us some of the insight into the failures that we were seeing, and also just to get better insight, as Ruslan had pointed out, to just how are the resources utilized during the run and across the entire cluster. So a few things that we came out for requirements that we wanted to address here. One was that we've got this cluster-wide processing. It's a distributed system. We need to be able to monitor across the entire cluster. We're interested in each node and each process within each node to be able to get a better insight into how the memory and CPU is being utilized. We're specifically interested in high CPU and high memory as part of the characterization, both from the perspective of identifying problems, but also to give us some information as far as our production process is concerned, to be able to help characterize these jobs and understand how they perform. We wanted to record the whole process hierarchy under Yarn for all of the Spark jobs and the timing associated with that, when the jobs were spun up, how long they were running. And as I mentioned with the production releases, we want to be able to have some traceability as well, where we can go back and compare the memory usage for a given algorithm in a current release versus past releases to make sure that changes and optimizations that we may have added won't actually negatively impact the memory use or the CPU utilization. We also had an underlying interest in integrating with the rest of our internal processes and harnesses so that we could put that as part of our general development process. So with this cluster, we already had in place a system that we used that was a very simple Django Apache system with a MySQL database behind it. And we used that to log a number of the standard performance metrics. So we had a performance harness that ran on a performance test system. That was basically a collection of scripts that allowed us to both deploy the test system, deploy all of the nodes, provision them, set up Hadoop, and then install the Squirrel software, and then also execute the tests themselves and collect various metrics and store those in that MySQL database. And the Django Apache server also provided a simple front end to be able to go in and report on those measurements. That also provided us a way to annotate those runs with some data about the system under test, so we could identify which release, what build it came from, what branch, what day, and so on. So the scripts themselves, there's this basic performance harness, which is the executive for the entire run. It simply makes a request to the REST API on the Django server to get a run ID. This allows us to just aggregate all of the various results against that run ID for reporting purposes, and also to tie it back to, again, that metadata associated with the run environment for the for the test, the cluster, the software versions, and so on. Once it's got that run ID and it started the tests and set up all the environment, it can then go off and spin up a process monitor script on each of the data nodes. The whole performance system is just run from a config file, so it can be pointed at whatever cluster we want to test. So this is a generalized solution for our testing environment. But the process monitor gets spun up, and it's started on each of the cluster nodes. And the other piece that this script does is actually initiate, through the Squirrel server, initiate the jobs that will basically start up the Yarn jobs to run Spark applications. There's also a logging table that's tracked that allows us to annotate events within the run. This allows us to correlate the start of a Spark job, for instance, with specific process data that gets logged. Each of the process monitoring scripts, it's a very simple script. It is running every 10 seconds. The main interest is these high CPU, high memory utilization applications. So for that reason, 10 seconds is a reasonable interval. It's arbitrary that we picked that. Because it's running on Yarn, the script simply looks for the node manager process and recursively pulls all processes underneath that and collects all the process data and logs it into the MySQL database. And again, this is all associated with a specific run ID just for the reporting purposes to make it easy. The database design, this is not a complete image of the full database. It's just the pieces that are appropriate for this. We have a number of other tables that are capturing things like performance metrics, actual process data. The run, this is, again, a little bit called down to just show start and end time. There's some software version information that's also captured, who ran it, the suite, the overall status of pass and fail. And then the process monitor table, which is the primary logging for all of that process monitor script, all of the CPU and memory statistics. And then the logging database is simply there for being able to do those annotations and to provide a correlated way to tie time ranges of process data with specific Spark jobs that ran. The user experience is really simplistic. This is a very simple Django app. It presents, this is a little call down, but it presents you a list of the runs and where the performance data was set up to be collected. It will provide a link to that. That link will drill into the individual jobs that have been started by the performance harness. One of the key things was as part of the Squirrel job may be multiple steps. There may be a bulk load and extraction process into a graph model that happens in MapReduce. And then there's a series of Spark jobs that will run after that. So this provides a way to drill into any one of those jobs to get the various process data. Even though we're focused on the Spark performance here, this is a generalized collection. So it simply pulls everything under Yarn. So if it's MapReduce, it'll collect all of the processes that are associated with that as well. And once you drill into that, then it can provide a graphical representation of the top memory or top CPU processes as needed. This is showing, again, because this is multiple steps, there's a bulk load and extract process and then other Spark jobs. It's highlighting processes that are related on the top with a specific set of Spark jobs that were run. And you can see some spikes in there. And this specific run was the one of interest that Ruslan is going to continue on from here to describe how this particular run, the data from this, provided us some insight to be able to debug.
All right, thank you. So yes, as now that going back to our issue, I call Ed, he comes for rescue with his tools, and we're setting up another run. If you Google about out-of-memory errors, Spark out-of-memory errors, the typical solution is increase the size of your containers. And so we did, all right, and we ran it, and at that point we started monitoring. And what we saw was that on the driver, we have these memory spikes. So when the size of the container on the driver was below this memory spike, we would be running out of memory. So that, beautiful peaks, and we really could not, first reaction is still, why is it happening? So we correlated that with the part of the code that is loading trained models into Python. And this is, surprisingly, that was happening only on the driver. Even the same models were broadcasted across the cluster, so they would be used in the, each executor. And executors did not have a bigger size than the driver. So it was a little bit mysterious. So further investigation revealed the following picture. So if you're not familiar, then pay attention when you use PySpark, is that there is a very complex interaction between Python and Spark. First of all, Spark is written in Scala, and Python, it really provides you only an API. And so when you're running your PySpark script, at the same time when you're launching the Spark context in Python, a JVM with the actual real Spark context is launched. And all the command that all the API calls that are being done in Python are translated through socket using spitefulJ library into the JVM, into the driver JVM, which builds the DAGs and then sends the instructions to the executors. On executors, the picture is somewhat different. On each executor, you have JVM that is running against Spark, and as it receives the instructions, it launches the Python processes in order to do the actual work on the executor. So this architecture is very important because in our case, what was happening was that we were loading encrypted trained models from HDFS into Python. In order to do decryption, we use Java libraries, and therefore we use the spitefulJ to execute that call. So what happened was the trained model would get into JVM, would be decrypted, and then sent through the socket using spitefulJ. There is not a problem with that, except that the protocol that spitefulJ is using would inflate the size of the transferred byte array by a factor of 100. So at that point, that was the spike. Only in translation, a model that was 20 megabytes would become all of a sudden 2 gigabytes, etc. So that was non-trivial revelation to all of us. And the solution ultimately was to implement a custom protocol for loading data from Python to JVM on the driver. But this is just to give you an insight in not only the Spark's architecture and how Python interacts with the JVMs in it, but also that this type of problems will happen. Even though we solve this problem, there will be others that we do not anticipate as of yet. But monitoring tools like the one that Ed presented are really incredibly useful. All right, so now we have our solution. We implemented it. Back to the square one, we need to test it and verify that everything scales well. We perform the same run again. The same plot tells us now that all the issues are gone, right? The spikes disappeared, made us very happy, and then we rolled it into production. So that was sort of a happy end of this story, but it was a bit stressful in the middle of it. Anyway, so I think we're gonna wrap it up. So what have we learned in the whole process? First of all, is that yes, Spark applications scales, except that don't take that for granted. You really have to, first of all, when you design your code, you really have to understand the Spark's architecture, and in particular, if you're writing a Python applications, you need to understand the Python JVM interactions. Follow the normal best practices, use iterators but not lists, be careful with joins, all the usual things, lazy evaluations, etc. And ultimately, what you want to do is you need to understand your computing demands. So you really have to have some sort of a tools that tells you about that. Test at scale is extremely important. Really, you cannot rely until you really test it at scale that your application is ready for production. That requires investment in tools, but ultimately it really pays off. So if you sort of really approach that problem as debugging complicated distributed application, it totally makes sense. So ultimately, if you have all of this pulled together, you test, your code has been tested, then you're really in good shape and you can roll into production and your code will shine and your customers are going to be extremely happy. Right, this is all for me. This is our contact information. Please feel free to ask questions later after the session. Also send us emails. We are not sure whether this is interesting to a broader community. If it is, let us know and we'll be very happy to collaborate. All right, thank you very much.
Questions, please?
So I have a question related to the performance hit that you have with logging every process. Do you guys experience something around that, and what is the volume of data you are storing for the logs in your MySQL server?
Yeah, so the volume of data is really only in the tens of thousands of measures. It's looking at Node Manager and below. These scripts typically run on the order of a half an hour to a few hours on most of the scale runs that we do for this type of characterization.
You're talking about the data that we process or the data that is required by these processes to monitor?
What you're logging.
The loggings.
Say that again?
What you're logging, the data that you're logging.
Yeah, so the logging is, as I say, it's a given run is probably on the order of tens of thousands of measures in the MySQL database. So, I've used these for a long time with millions of rows without any kind of real issues. So this is relatively small. And the advantage with the way that it's set up is the logging data gets put in there. It's all associated with a run ID. If we want to do some housekeeping later, all we have to do is identify the runs that are of interest to us to retain for historical reasons, for release requirements and things like that. We can clear out a lot of the stuff once it's done and not have any real consequence there.
Any further questions?
So I was just curious to what extent this was specific to Squirrel's product, because it seemed to be most of what you were describing was generally applicable to at least machine learning workloads, if not all data processing.
That's right. It's, that part is not specific to Squirrel at all. Actually, any Spark application, not even machine learning, can benefit from it. But machine learning, especially because of all the complexity. Yeah.
Just curious, did you guys find it useful, or did you ever consider indexing this using, Splunk or Elasticsearch or something like that, like for searchability?
Yeah, our search is not worse. No, the point of this is that this is really, there are several implementations of the distributed key value stores, and this is one of them. It has all the same properties. So, yeah.
One more question? Anyone? Oh, right at the back. Okay.
For a lot of the state that you guys are presenting, it's really cool state for debugging Spark. How does this compare with Yarn work for like application timeline service, especially the V2 work that's proposed and underway?
I'm actually not familiar with it, so maybe we should talk afterwards.
That would be great.
Okay, well, thank you very much. Please show your appreciation. Thank you.
Great, thank you.